Hi guys, thank you for joining me in this video. I will go through a few examples on axial deformation in the members. For the rigid bar, AB is pinned at A, pin support at A, and supported by two aluminum rods CD and EF, each having a diameter equal 1.1 inch. The modulus of elasticity of this material is 10 times 10 to power 3 KSI, and the yield stress is not a big deal. If the bar is initially vertical, determine the displacement of the end B when the force of 20 kb is applied. Looks like point B will move horizontally. So first of all, I will start with the engineering mechanics part to figure out one of the equations. So this free body diagram, the vertical bar is hinged at A. So I will have two reactions. I don't care actually about them, XA and YA. The rod CD will apply a force in this direction F CD. The rod EF will apply a force in this direction F EF. And we have applied force in this direction, and this is the reason why I assumed CD and EF on the left, because the applied force on the right, 20, at point B. We have equilibrium equation, summation f of x, summation f of y, summation moment. Summation f of x equals 0, it's not a big deal. Summation f of y equals 0, it's not a big deal. I will take moment at A. I'm gonna assume this positive direction is clockwise equals 0. So if you take moment at A, XA and YA will be cancelled. We don't have distances for them. So I will have negative FCD, it's counterclockwise, time the vertical distance 1 feet, plus negative FEF, the rotation is counterclockwise, so it will be negative, time the vertical distance 3 feet. Positive, the force 20 will be positive, time the vertical distance, which is 4 feet, equals 0. From this equation, I can say FCD plus 3 FEF equal 80. This is the first equation we can derive from engineering mechanics. Keep in your mind, I'm looking for what are the forces in this rod. What is the force in this rod? So this is my focus. So I don't care about summation f of x. I don't care about summation f of y, because f of x and f of y will include xa and ya. I don't care about them. My concern only about FCD and FEF. So this is the reason why I focused only on the summation of moment at A equal 0. This is the first step. Second step, keep in your mind, this vertical bar, which is hinged at A, and we have applied force 20 kb at this end, I expect the movement or the deformation of this bar something like this. Keep in your mind, originally we have a rod here and we have another rod here. So I expect elongations in this rod. I expect elongations in this rod. So this is the elongation in rod CD, delta CD, and this is the elongation in rod EF. This is delta EF. Does that make sense? And this is the movement at point B. This movement will be the delta at B. Keep in your mind, this rod EF, and this rod CD, the delta in these rods, delta EF, equal the applied force PL divided by AE. So the applied force in this rod EF, the length of this rod equal 1.5 feet. The cross-section area of this rod is pi divided 4 times diameter squared. The diameter of this one is 1.1 inch square. Time Young's modulus of this material, which is 10 times 10 to power 3 KSI. 10 times 10 to power 3 KSI. I will adjust the units. So this one in inch square, this one in kib per inch square, this one in feet. So I will multiply it by 12 to be in inch, and this one will be in kib. We are good. So this elongation should be, this elongation should be 1.5 times 12 divided by divide 4 times 1.1 square times 10 times 10 to power 3. This number equal 0.0019 FEF. That makes sense? So I found the expected elongation in member EF as a function of the force in this member. The same, I will repeat it with the elongation in member CD will equal PL divided by AE. So the applied force in this member CD will be FCD. The length of this member is also 1.5 feet. The cross-section area, the diameter is 1.1 inch. So it will be also pi divided 4 times 1.1 inch square. The Young's modulus of the material will be the same, 10 times 10 to power 3. So I will multiply this value by 12 to convert it to inch. So the final value will be 0.0019 FCD. So I found the expected elongation in member CD as a function of the applied force CD. That makes sense? If you look to this deformed shape, I can say I have this triangle. This is point A, this is point B, this is point E, this is point C. So this movement will be delta B, this stretch will be delta EF, and this stretch equal delta CD. We can set up triangle similarity between this little triangle and this bigger triangle. So I can say this distance AC, which equal 1 feet, divided by this total distance, which is AE, 3 feet, will equal the delta CD divided by the delta EF. So what I did, this length divided by this length equal this distance divided by this distance. So I can say delta CD will equal 1/3 delta EF. And that makes sense. Delta CD will be 1/3 of delta EF. Go ahead and remove the value of delta CD. Delta CD equal 0.0019 FCD equal 1/3 time the value of delta EF equal 0.0019 FEF. If you simplify this equation, I can say FCD will equal 1/3 time. I can remove this one by this one, so I can say FCD equal 1/3 FEF. That makes sense? This is the second equation. Keep in your mind, we have a first equation from engineering mechanics. Summation moment at point A equals 0. I set up this equation. From the compatibility and the deformation, I figured out the elongation in member EF, the elongation in member CD, and I set up this deformed shape, and I find out triangle similarity. So I find out the relationship between delta CD and delta EF. I found the force FCD equal 1/3 the force EF. Remember the original equation FCD plus 3 FEF equal 80. Does that make sense? Equal 80. So I can remove the value of FCD and put 1/3 FEF. I think the only unknown in this equation will be FEF. So I can say FCD, yes. FEF will be 1/3 plus 3 divided by 80. So the value of FEF will be 24 kib, and the value of FCD will be 8 kib. So the force in this member EF equal 24 kib. And the value in this one will be 8 kib. That makes sense? So I can now find out what will be the elongation delta EF. Delta EF will be 24 times 0.0019 equal 0.0456 inch. And the elongation CD will equal 8 times 0.0019 equal 0.0152. But this is not the requirement. The requirement in this problem, we are looking for what is the horizontal displacement at the end B. What is this value? You can set up another triangle similarity. For example, the biggest triangle with this little triangle. That makes sense? So I can say this bigger one, this distance is delta B. I don't know how much. This vertical distance is 4 feet. And this little distance equal 0.0152 inch. And this little distance is 1 feet. So I can say 0.0152 inch divided by delta B will equal 1 feet divided by 4 feet. So the delta B will equal 0.0608 inch. This is the displacement at the end B for this problem. So this problem is very interesting. We solved it with different parts. The first part, engineering mechanics. I set up the free body diagram, take moment at A. So I found the equation as a function of F, FCD. The second one, I draw the deformed shape, the expected deformed shape. Since we have 20 keep pushing or pulling this point to right, so the new deformation for bar AB will be like this. That means this member stretched by this distance and this member stretched by this distance. How much stretch in each bar equal PL divided by EA. Then I set up triangle similarities to find out a relationship between the stretch in this member EF and the stretch in this member CD. So I set up another equations as a function of FCD and FEF. I solved the two equations together to find out what is the force in member EF, what is the force in member CD. Once you get these forces, I can go back and find out what will be the stretches in these members. But this is not the requirement. The requirement is how much displacement at point B. So I set up another triangle similarity to find out what will be the displacement at point B. One more example. We have this example. We have a beam AE. This beam is hanging out by three link members or three rods, A, B, C, D, E, F. And this beam is supporting a force 15 kilonewton. We are looking to figure out what are the forces developed in each bar, bars A, B, C, D, and E, F. I will solve this problem also in the same way like the previous example. First of all, I will set up the engineering mechanics part. We have this beam with applied force here, 15 kilonewton. This bar or this beam is supported by a force in this bar EF with a force in this bar CD with a force in this bar AAB. So I will have FAB, I will have FCD, I will have FEF. That makes sense? Okay, so if you apply summation f of x, I don't care about summation of x because we don't have any forces in x direction. Summation f of y equals 0, I can say FAB plus FCD plus FEF equal 15. I will take moment at E. If you take summation moment at point E equals 0, I'm going to assume counterclockwise is my positive. So taking a moment at E will cancel FEF. So I will have FCD negative time horizontal distance 0.4 meter. I will have positive 15 kilonewton time horizontal distance 0.6 meter. I will have negative FAB time horizontal distance equal 0.8 meter equal 0. This is the second equation. I cannot do anything more. So summation f of y, summation moment give you two equations in three unknowns. I'm sorry, two equations, yes, in three unknowns. I cannot solve them because the summation f give you equation with three unknowns. Yes, summation moment give you equation with two unknowns, but I cannot do anything more. So the next part, I need to figure out how or what is the deformation of the beam AE. So keep in your mind, this beam is hanging by this bar and this bar and this bar, and we have a force here. I think this force will cause more deformation in this one, a little deformation in this one, a little deformation in this one. So this is the new shape of your beam. We have here delta, we have here delta, we have here delta. This delta will be AB. This one will be delta CD. This one will be delta EF. That makes sense? This horizontal distance equal 0.4 and this horizontal distance equal 0.4. So I can keep in your mind, let's do this first. The delta in member AB will equal the force in member AB times the length of this member, which is 0.5 meter, divided by the cross-section area by divide 4 times diameter of this bar. The diameter of this bar is, we don't have the diameter, but we are given the cross-section area, 50 millimeter square for AB. So the cross-section area is 50, is given 50 millimeter square. And the Young's modulus for the material, the Young's modulus is not given. So for steel A 36, Young's modulus E equal 30, I'm sorry, wait, equal 200 gigapascal. So I need to adjust the units first. So this one in meter, I will multiply it by 1000 to be in millimeter. This one in millimeter square, we are good. This one is gigapascal. I have to multiply it by 1000 to be in megapascal, which is Newton per millimeter. That means the force will be in Newton. That means the force will be in Newton. Or since this force in kilonewton, we have another option. I can remove this 1000 and keep it in gigapascal. That means this force will be in kilonewton. That will be good. So delta AB will equal 0.5 times 1000 divided by 50 times 200 will be 0.05 FAB. I can figure out the delta in CD equal the force in CD times distance or the length of this member 0.5 divided by the cross-section area of member CD, which is 30 times 200. I will multiply this one by 1000. So the delta in CD will be 0.5 times 1000 divided by 30 times 200 equal 0.08 FCD. The same delta in member EF equal the force in member EF times distance. The length of this member is 0.5 meter divided by the cross-section area of member EF, which is 50 millimeter times Young's modulus 200. I will multiply this one by 1000. So the delta EF will equal 0.05 F EF. This is the value here, the value here, the value here. That makes sense? I will set up a triangle. This is the reference. This one moved down a little bit, moved more, moved more. This is the new position of the beam. That makes sense? So we can say, I will set up this triangle. What will be this value? I'm sorry. What will be this value? This value will equal delta CD minus delta EF, because this one is delta EF. If you subtract this value, which is here, you can find the value delta CD minus delta EF. And this value will equal delta AB minus delta EF. And I can say this triangle is similar to the biggest triangle. So I can say delta CD minus delta EF divided by delta AB minus delta EF equal this length is 0.4 divided by the whole length, which is 0.8. Is it correct? Yes. Does that make sense? Or equal 0.5. So I can say delta CD minus delta EF equal 0.5 times delta AB minus delta EF. If you simplify this equation, so I can say delta CD plus minus delta EF, and we have the positive, so 0.5 delta EF minus 0.5 delta AB will equal 0. So go ahead and remove delta CD and put this value. Delta CD equal 0.08 FCD minus 0.5 times delta EF. Delta EF equal 0.05 FEF minus 0.5 delta AB equal 0.05 FAB. Equal 0. If you simplify this equation, I can say divide it by 100 maybe, or multiply it by 100, so it will be 8 FCD minus 0.5 times 0.05 times 100 equal 2.5 FEF minus 2.5 FEB. This is the third equation. So right now, we have three equations. This one, and this one. You can solve the three equations to find FAB, FCD, and FEF. That makes sense? Once you get the forces in these three bars, you can, this is the requirement. The force developed in each bar. Once you get these forces, you can go back and find out what will be the elongation in each bar. Once you get the force, you can multiply it by 0.05 to find out the force. That makes sense? So this is a homework, how to solve these equations together, three equations in three unknowns. Once you solve them together, you can find out the required forces.